Okay, thank you again for this talk. So our next speaker is going to be joining us remotely as we're going to be moving back into quantum education. So Chandralekha Singh is a distinguished professor of physics at the University of Pittsburgh and is a national and international leader in the field of physics education research. And among many other things, Dr. Singh and her research group has been studying students learning of quantum mechanics for over 20 years. So we are excited to welcome her virtually to Mason, and this talk is on preparing students to be leaders of the second quantum revolution.
Thank you so much for having me here. I'm delighted to join by Zoom. Wish I could be there in person. So, just wanted to start out by saying that the first quantum revolution gave us lots of interesting things, including the computer that I'm communicating with you with, lasers, nuclear technology, and now this new excitement abounds because of the fact that we are able to manipulate quantum phenomena, actively creating and manipulating and probing quantum states of matter in the way that we have never been able to do before, taking advantage of superposition and entanglement. And there are so many amazing applications that we are envisioning in quantum sensing, simulation, computing, and communication. So 3 years ago, a little bit longer than 3 years ago, Office of Science and Technology Policy at the White House and National Science Foundation put together a group of people from academic fields, also like industries and national labs, to think about, what are the key concepts that all students, including those in K through 12, should know about quantum information science and technology. So basically, this group met in March of 2020. And in fact, we were supposed to meet in person, but it turns out because of the pandemic, we met remotely. So this workshop took place remotely. And these are the key concepts that we came up with. Things we feel that even in the K through 12, students should learn about quantum states, quantum bits, quantum measurement, entanglement, coherence, quantum computing, communication, and sensing. And of course, it needs to be done at the level where it's commensurate with students' prior knowledge. So there needs to be good impedance matching between what the students knows and what they are learning here. And so, we actually now have worked over the last 3 years with K through 12 teachers. So we have worked with high school physics teachers, chemistry teachers, computer science teachers, and mathematics teachers, as well as middle school teachers, to expand upon these things and come up with a framework for how in K through 12 quantum education can actually be, how quantum can actually be taught. So if you're interested in those things, you can find them on the Q12 National Partnership website. And if you're having difficulty finding it, please do let me know. So this was the report that came out 3 years ago on those key concepts. And as I said, now we have an entire framework for high school and middle school. And if you're interested, please take a look. And we are also looking for feedback from people because we are thinking of it as a living document. So as I mentioned, the National Q12 Partnership and Q2 work is basically supported by National Science Foundation, and the PI for this grant is Emily Edwards from University of Illinois, and Diana Franklin and I are the co-PIs on this particular grant. So basically, we have a lot of partners here, and this partnership, has monthly meetings actually, where people come together and brainstorm different issues about how to actually strengthen the partnership between industries, national labs, and academia, and also how to support and promote quantum at the K through 12 level, both through like formal teaching, where we are supporting the teachers and helping them with professional development, and also informally through outreach and other activities. So basically, the question is, why should we worry about quantum at the K through 12 level? And so we can see that quantum is this transdisciplinary field where you actually have people from lots of different disciplines coming together. So you could be a cryogenic engineer, or you could be a quantum software engineer, or a physicist, or program manager, a quantum algorithm researcher, electrical engineer, policymaker, computer architect, systems engineer, business developer, teachers or professional development people who do professional development. You could be person in nano fabrication, or vacuum technology, or a chemist, or a mathematician, or a material scientist. I mean, it just goes on and on and on. And in fact, Tim Akers and Kevin Peters just described very nicely, some of the things that people could do, even if they are really on the periphery of quantum physics. So quantum in general. In other words, you don't have to actually be at the center of it, making the qubit, thinking about how to do quantum measurement, or how to actually do the evolution gating of quantum gating, but you could actually support these people in many different ways. And so this is a field in which we can actually get students involved and excited about, because this whole era is going to be an era where we are going to see a lot of very interesting things happening in this area. And in fact, industries are already saying that they do not have enough people to do various things. So in other words, like we already have, dearth of people working in these areas, and we definitely need to get students excited. And what better way to do it than to do it in K through 12, when we have a lot of students who actually could get interested in these areas once we tell them about the potential of these fields in the next century. Because, for example, making robust qubits, thinking about good ways of doing quantum measurement, or thinking about ways to gate quantum system. I mean, we don't even actually have a computer architecture that is really the stable architecture that is what we are going to have going forward. So there's a lot to be done. Quantum error correction is going to be something that's going to be key. And so, like this whole century, we are going to see so much growth in this area that it's really important to think about how to get students excited about this early on. And if we really think about only the college students, because I'm a college professor, and the point is that if you only think about those people, we already have missed out on a lot of people, especially, the diversity of the student population is mainly there at the K through 12, and in the college level, that already decreases many-fold. And so if we start having children excited about it early on, that's going to be a really great thing. And also, if the students start learning these things early on, right, that's also good, because they're not going to think of quantum as a spooky thing. They're not going to think of it as something that totally doesn't make sense, because it's true that the framework of quantum physics is very different from the framework that we are used to, the classical physics that we are used to. But, if you learn both languages at the same time from an early age, it doesn't seem very surprising to you, or it doesn't seem like something that is totally incomprehensible. I mean, I'll give you an example from my own upbringing. Like my mother tongue is Hindi, not English. But the thing is, I learned English from when I was little. And so, like even though I was learning two languages at the same time, which are very different from each other, I didn't really think that they were really that difficult to learn. On the other hand, if I had not learned English, like from when I was little, then I would have actually had great difficulty learning it. So something that you learn from early on, you sort of know when to switch modes and when to think, in Hindi and when to think in English. So similarly, if we actually start introducing students to the quantum paradigm, in a way that is still connecting with their prior knowledge, it's commensurate with the kinds of things that they are learning, not necessarily too mathematical, but like you maybe make it for graduate students, then you are going to actually make students think about these things in a way that would actually, be exciting, and they would actually learn both the classical and quantum paradigms at the same time, and not find the quantum paradigm as spooky as people do right now. So I think that, the goal of the National Q12 Partnership is to grow the connection and cohesion between the quantum education community and the industry and national lab experts, and also to have a national hub where people can actually give us their materials, and we can actually make it available to everybody. So for example, today is World Quantum Day. So, basically, there are lots of activities like quantime activities that teachers can actually do. These are canned activities related to quantum that can be done in K through 12 classrooms that are already available in this on this website. It's q12education.org. So if you're interested, you can actually go and take a look. And of course, we have the frameworks that I was telling you about that are expanded version of those key concepts. So I already told you about the benefits of starting early. And I truly believe that we should really be thinking about starting early when the diversity in student population is a lot more, and we can get students from diverse groups excited, just like the way Tim and Kevin were already talking about, and they will think about careers, that could be very different kinds of careers. Like, as I said, you don't have to be the person who's thinking about making the qubit better, like making the qubit itself more robust, or thinking about how to make quantum gates better, or how to make the measurement process better. But you could think about all the peripheral things that are needed, such as helping with the electronics, helping with the cryogenics, helping with the vacuum technology, helping with programming or troubleshooting aspects, or nanofabrication, even like management or communication, because the misinformation has increased so much that we really want people to actually give the right kind of information about quantum to the public. So, since I mentioned diversity, equity, and inclusion, I would like to elaborate on some of the issues. So if you look at this picture, this is from the famous 6th Solvay conference in 1927. And this is basically, these are all the founders of the first quantum revolution 100 years ago. And one of the things that you should notice about this, I don't know what you're noticing, is that there is only one woman in this picture, and everybody in this picture is white. So that's one thing that should stand out to you in this picture. And if you look at a picture from a physics conference recently, this looks only slightly different from that one, not significantly different. And then you should think about, why is it this way? Are we really missing out on the potentials of all of the people who are not represented in these groups? And the point is, can we afford to actually lose out on their talents and expertise? This is a really important question that Kevin and Tim had already asked, because the other thing is that, as you can see, our country is becoming more diverse. We need to really exploit the talents. If we don't really think about it, we are going to miss out on the on the competition that's taking place in the global arena. So let me, before I actually describe diversity, equity, and inclusion and its importance in quantum much more, I wanted to actually put out for you what I really mean by the word equity. So in my mind, equity in learning in quantum has 3 components. One is that everybody should have equitable opportunities. So they should have, quantum education, educational materials and learning tools should be available to all students, and they should be commensurate with their prior knowledge and skills. Also, the learning environments in which these students are should be equitable and inclusive. That means that they should have guidance, support, and mentoring as appropriate, and everybody should have equal sense of belonging regardless of their background. And it is really important that all students are looking forward to embracing their challenges and use it as a learning opportunity, as opposed to being threatened by the challenges. Because if we don't make learning environments equitable and inclusive, then students who come from historically marginalized backgrounds, students who have had disadvantages, they are the ones who are actually going to otherwise not feel like they belong. They might wonder whether they have what it takes to excel, and they might be the ones who are actually who are going to drop out. So I want to put out a framework where also learning outcomes are equitable. What I mean by that is that everyone has good learning outcomes, and if you look at it by demographics, all demographic groups do equally well. And if some people have historically been left out and they've gone to schools that have failing infrastructure or teachers who are not well prepared, we need to think about ways to actually give them intentional support and center their experiences so that all of those things are actually remedied and all of the people have equivalent outcomes regardless of their demographics. So all the groups on average have similar outcomes. And as I said, it requires intentional allocation of resources and structuring your classes or extra help session and everything that you have on all your resources in a way that is equitable, instead of focusing only on those people who have already been ahead. So let me show you the current situation here, because if you think about quantum in general, several fields have come together here, right? Like physics, computer science, and electrical engineering. And if you look at these fields individually, you can see physics has 20% women, computer science 20% roughly, electrical engineering has 14%. And if you look at students from historically underrepresented race and ethnicities, it is even worse. Like, for example, I'm showing you here the data from electrical engineering. And when you look at it, you can see that, while the number of electrical engineering majors every year has been increasing from 2011 to 2017, those who are historically underrepresented racial and ethnic minority groups, their numbers have not increased very much at all. So that means we are doing a really poor job of supporting students and getting them excited about these areas. And I want to see that this second quantum revolution, this new field of quantum information science and technology, has a very different feel to it than these fields like physics, chemistry, electrical engineering, and computer science that have come together to form this new field. And one of the good things that I think that this new field has going for it is that nobody can really claim to be a real expert in all of the different aspects of quantum information science and technology. You might be a physicist, but you may not know all about quantum algorithms, or you might be like a chemist, but you may not know about some other aspects. So the point is, in that particular case, I feel like, there is a hope that the culture of quantum information science and technology is going to be much better and more equitable, that is supportive of all students, compared to physics, electrical engineering, and computer science, where the norms have set in and people are not recognizing that they have a role to play in making the learning environments more equitable and inclusive. Let me just give you an example of what happens, because I do a lot of research in these areas. And one of the things that we have found is that even things like this here, I'm just giving you an example. It says a student asks a professor how to solve a quantum problem, and the professor starts laughing and says, "Oh, this is a trivial problem." Now, notice that what is important is not a professor's intention, but the impact that they are having on the student. And if the student is actually from a marginalized background, historically marginalized background, they're more likely to think of this particular response from the professor to be like a slap on their face. They're like, "Oh, I struggle with this problem, and that's why I came to you in my office hour to ask you about it, and you're saying this is trivial." This also creates what people call stereotype threat, which is threat of, conforming to a stereotype about oneself, whether it's like women in physics or computer science or quantum overall, or whether it's, a racial ethnic minority groups who have historically been underrepresented in these disciplines. And the awareness of this stereotype, that this person is saying this is trivial and it's not really trivial for me, makes it very taxing for people, and they start wondering whether there's something about them that is making them struggle. And people can start saying, "Oh, I'm struggling because I'm not as good as these other people. What's the use of even trying?" So they start, and also cognitive science says that some of your cognitive resources, if they're taken up by the anxiety, if they're robbed by the anxiety, you have less cognitive resources to really do problem solving and learning about quantum and other disciplines that actually comprise this field of quantum information science and technology, especially because your working memory when you're trying to solve a problem is fixed, and you have only 5 to 9 chunks regardless of who you are. And if some of it is being robbed by the anxiety, because of the fact that your people who are teaching you are not creating an environment where you feel like you belong, whether you have what it takes to excel, if they're not making it clear that they have high expectations of you, but they know that you'll meet those expectations by working hard, working smart, taking advantage of all the resources, and working with other people, going to office hours and stuff like that, then they are the ones who are more likely to actually quit. So I'm going to show you some data from my own research, and this is basically research in physics courses. This is a 2-semester physics course at my university, and what I'm showing to you on the vertical axis here is the self-efficacy, which is students' belief about how good they are in solving physics problems. And in the horizontal axis, I have like students' grade And this is the A grade, B grade, C grade, A, B, C. What you see here is what happens to men and women. And what you see in Physics 1 is that at the end of Physics 1, women who actually get A grade have the same self-efficacy as men who have B grade. And by the time you get to Physics 2 end, actually women with A grade have the same self-efficacy as men who have C grade. So in other words, the gap between the historically marginalized people and majority people has actually increased instead of decreasing. This is not an example of an equitable and inclusive learning environment. The goal should have been to decrease these gaps as opposed to increase it. So you can see, by the way, I also must say that your grade is not the only thing that matters, but your belief about how good you are at solving problems is really important. So people will quit a discipline because they have lower self-efficacy, even if they were actually getting good grades. So let me actually show you these data. And this is for students in computer science and engineering. This is basically their STEM GPA on the vertical axis. Sorry, this is their overall GPA on the vertical axis on this side. And this is their STEM GPA. And this is which year in college they are in. And what you see on the top are women who actually completed computer science and engineering. And you can see that they have a higher grade than men who actually finished computer science and engineering. But what I want you to focus on are these two curves, because here you see women who quit their pursuit of computer science and engineering majors, and here men who quit their pursuit. And what you see is that there is a huge difference in the grade, and women are dropping out with significantly higher grade than men are. So now you might ask, why are they dropping out? And you can come up with a deficit model and say, hey, they realized that they didn't want to be there. No, why don't we actually reflect upon our own role in doing this and recognize that we did not create an environment where these people had high self-efficacy. These people had a high sense of belonging. These people felt like, they were doing well. And so, they are more likely to drop out if we don't do anything about supporting these people. And you can see the same kind of trend is actually there even in their STEM GPA. In fact, in some cases, you can see here, women who drop out have the same GPA as men who actually stay in these disciplines. So let me actually also show you, this is similar kind of data for math and physical science majors. So this is physics, chemistry, and math. And you can see similar trends even here. And the STEM GPAs are sort of reflecting the same thing here. So you can see that these things are showing inequities in our system. And I'm also showing you here the percentage of students who drop a particular discipline versus the different disciplines named. So this is bioscience, computer science, engineering, math, chemistry, physics, etc. And what you see is that physics has, for example, 38% of all students who declare a physics major drop out. But when you look at the underrepresented minority students, what you see is that this is 65% in physics. This is a horrible thing, because these are people who love physics. They wanted to be here, and we actually didn't do anything to support them. We let them go. How are we going to actually make sure that we are ready for quantum if we really let all these students who actually declare these majors leave because we are not willing to actually create an environment in which they feel like they belong, in which they feel like they have high self-efficacy, where they feel like they have an identity as a person who can excel in STEM. They have actually a mindset where they know that it's all about working hard, working smart, and failure is not really failure, but an inevitable part of getting ahead and learning. Because even Einstein said, if you haven't failed, you've really not tried to learn anything new. But if we don't convey to students that, struggling with challenging things in these disciplines is actually a normal part of learning, everybody goes through it, and this is how you actually get better at something, then the ones from marginalized backgrounds are the ones who are going to actually think that there must be something about them that is making them struggle, and everybody else must have everything figured out. So basically, my thing is that if we really want to excel in quantum and keep the leadership in these areas, then we need to really think of ourselves as a coach for the student, where we not only as a coach in tennis or say chess, you are not going to worry about helping students with offenses, but also with their defenses. What I mean by that is that we are going to actually make sure, we have to make sure that we help our students become efficient problem solvers, be able to transfer their learning from one situation to the other, help them develop robust conceptual understanding. But at the same time, we also have to make sure that their defenses are strong. That means we have a learning environment in which they have all students have a high sense of belonging, regardless of whether they are from traditionally marginalized group. They have an identity as people who can excel. They have growth mindset about their potential. That means intelligence is something that can grow by working hard, working smart. It's not immutable. And basically your brain is a muscle, and it's good to struggle and it's good to fail, because failure is not really failure. And make sure that we have an environment in which students have a high self-efficacy. Because if we do all of these things, then students will also be more interested in quantum and other STEM disciplines that are related, and they will also have high achievement goals. So, and it's particularly important for those who have traditionally been marginalized in these disciplines, because they are the ones who actually otherwise will shut down and are not actually going to be able to communicate even in an active learning environment. Because our research shows that active learning in an inequitable learning environment actually increases the gap between minority and majority groups, because the majority group dominate in those situations, and the minority groups don't really want to communicate because they're not feeling safe, they're not feeling like they belong, they're worried about what if I say something and people will think I'm a woman or I'm a racial ethnic minority student. And so it's really imperative that we create an environment where everybody feels like, okay, I am here, and failure is a stepping stone to learning new things. I should be embracing it, because failure is not really failure. I should be patting myself on my back for not knowing something, because that's why I am actually here. Because if I knew everything, why would I be here? So, but it's really important that we create that kind of an environment. So let me show you data from a study that we have done, and this is all published, in which we actually incorporated a short intervention, which is called ecological belonging intervention, which is only 25 minutes long, that happens at the beginning of the semester. And this was initially done actually as a control study in which 3 instructors participated. And these are huge courses with several hundred students. These are physics courses. And several recitations participated as the intervention group. And then there was a control group. There were some control groups in which this thing didn't happen, and they were randomly selected. And basically in these recitations, the instructor emphasized the importance of struggling, and the fact that, they should be proud of struggling, because that means that they're on their way to learning new things, and they should be proud of doing challenging problems and pat themselves on the back, because it meant that they were on their way to learning. They should be working with their peers. They should be going to their instructor's office hour. And the idea was to reduce students' anxiety, reduce their procrastination, increase their enthusiasm for solving challenging problems, and ensure that the limited cognitive resources that they have is not robbed by the anxiety, but actually used to solve problems, right? And to actually struggle and learn from those experiences. And basically the instructor also talked about the fact that that's what they and other people that they know, all the other instructors also go through struggle all the time. And they did when they were students themselves. And so, I want to show you actually just data. I can tell you more about this intervention. If you're interested, just send me an email, but I can just show you that students actually who are from traditionally marginalized groups like women, they actually felt really good. So they came at the end and said, I'm so glad that you spent 25 minutes at the beginning of the semester on this. I'm feeling so much better. But if that was the end of it, it would already have been good. But what we also find is that, if you look at the average course grade, this is for the social belonging group. We don't find any difference between men and women. Whereas in the control group, in those recitations in which this thing was not done, there is a difference. So you can tell that the short intervention can go a long way. In fact, you also have to think about your own mindset as in terms of the potential of all of the students. And if you really think that all of the students have the potential to do well, then your students will do well. In fact, there is a study that came out in 2020 that was a study done with 150 STEM instructors in which they were asked questions like, to be sure, I think that only 30% of the class really deserves to do well in this course. Do you agree or disagree? What they found is that people who actually disagreed with those statements, they had growth mindset about all of their students. They thought that it was their job to help all of the students. And the gap between majority and minority group was really small in their classes, as opposed to those people who agreed with those statements and said, yes, only 30% of the class belongs there. So your mindset as the instructor of these students in these kinds of STEM courses makes all the difference in terms of how the students feel supported and the kind of interaction that you have with your students and the kind of learning environment you create and whether it's equitable or inclusive or not. Here I'm showing you the same data. This time for this one is for white and non-white students. And again, you can see that the orange is the intervention group and there's hardly any difference, very small difference between these two groups. Whereas in the group in which the intervention didn't happen, there is a much larger gap. In fact, the colleague who helped us in do this in physics also helped in biology. And there was also benefits in the biology courses for students when this short intervention was done at the beginning of the course. And by the way, the same kind of issues are also important when you are actually supporting your students in research, whether they are doing undergraduate research or graduate research with you. In particular, for example, I would say, if students are coming, first generation students or they're historically underrepresented, they are really worried about whether research goes in a straight line. So if they are not making progress in a few months, they might think, oh my gosh, they must be the worst research student working in your lab. They must really, not know what it's all about. But the point is that it's true that research never moves in a straight line. You move a little bit forward, then you go backward. You move a little bit forward, backward. If in 6 months you make some progress, you should already be feeling good about doing that. But if you don't communicate with students that that's the way research goes, and also don't actually make it clear to students that they are making progress when they are making progress and that they are doing a good job, students from historically underrepresented groups are the ones who are going to think that there is something wrong with them. And basically, and that can really hurt them. So I think that it's really important that you also think about these issues when you support your students. I think that I'm running out of time, so I'm not going to go into the work that I do in terms of improving quantum education, in terms of developing research validated learning tools. But if you go to my website, you'll see a lot of papers and materials. And if you need any of these things, please do let me know, because we are doing a lot of research on how to improve student learning of quantum physics. And these things are research based in the sense we think carefully about research learning objectives, students' initial knowledge. We do a task analysis based upon how an instructor will do something versus how a student will do, because we want to get all the expert blind spots cleared up. And then we develop these guided inquiry-based learning, teaching learning sequences, which we call quantum interactive learning tutorials and peer instruction tools, such as clicker questions. So for example, we just published something on quantum key distribution, which is basically about, how you can actually quantum mechanically, you can tell if somebody is eavesdropping when Alice and Bob are trying to generate a common shared key to encrypt and decrypt information. Because classically, there is absolutely no way to be certain that you are actually going, that somebody has eavesdropped. There could always be a hacker when you actually are not going to meet with a person. So if Alice and Bob were never meeting in person, classically, there is no way to confirm that somebody has eavesdropped. But quantum mechanically, you can tell. And so these QUILs, or quantum interactive learning tutorials, which are based upon research, really help students. And so students go through a lot of activities. There is also some computer simulations in these, and they actually work through various things that help them develop a solid understanding of these important concepts that they are actually that they should have a solid grasp of. So that's the kind of thing that I do. And we have written more than 70 papers on how to improve student learning of quantum mechanics. As I said, I've run out of time, so I want to invite you to go and visit my website for these kinds of materials. So at this point, I'll take any questions. Thanks so much. So I don't think I can hear actually anybody here. So maybe you can repeat it.
Can you hear me?
Yeah, I can hear you.
Okay. So, hi, Dr. Singh. I'm Dr. Vora. Thank you so much for that fantastic talk. I'm definitely going to follow up with you and pick your brain on a lot of things. I am going to open it up to questions from the audience first. Yeah, Mike.
I be heard. I don't know if I'm being picked up.
You might have to shout or come up here, one of the two.
So, you cited the study.
It's over here.
That's the
Also, I
microphone
think
right
you
there.
want to not be on that side.
Not if
Can you talk at the microphone?
Hello.
Yeah, I can hear you now.
You got it now. Okay, I guess I need to be right down here. One of the things I've noticed with my students, I try to tell them, you have to, like, in order to learn this stuff, you're gonna have to struggle a bit. That's part of the learning process. Obviously you're studying some studies here that I didn't know existed. What is this activity that, acclimates them to this? What does that look like?
So basically, like, as I said, it's a really short activity and anybody can do it really easily, but it also helps you think about your own mindset, about your own, about your students' potential. So basically you start the activity the way that we do it. We started by saying, we want to understand, your physics department wants to understand your concerns about being in this course. Why don't you actually write on the sheet of paper what your concerns are about being in this course, right? And students write a lot. And then we tell them, okay, stop now, like you don't have to give them more than at the most 10 minutes to do this. Then you can actually show them some testimonials from students in previous years. And these are real testimonials that we have actually gathered from students who actually also had similar concerns about being in the course. But then they realized that it was really about working hard, working smart, taking advantage of all the resources, patting themselves on the back for struggling, working with other people, going to instructors' office hour, being deliberate in problem solving, and recognizing that failure is not really failure, but a stepping stone to learning, and embracing those things and engaging with challenging physics problems, and making sure that they don't actually think of failure as failure, right? Because this is what happens to everybody. And so this is normal, and this is how you learn. And basically, some of those testimonials are from men, some of them are from women, some of them are from students who have white names, some of them are non-white names. And this is deliberate, that they're all saying in their same words, similar kinds of things. And then after this, students are asked to actually get together in groups of 5 and discuss what they wrote on that sheet of paper. And also, why don't students realize that struggling in solving physics problems is normal? This is how you learn. And why don't they realize that this is a good thing? This is why you are in college. And so the idea is that when you say, why don't you realize, you also want them to believe it, because the point is that's the way it's being framed. And notice that the instructor also talked about their own adversity while learning these things and how they struggle and how they continue to struggle now with the kinds of things that they are doing, including their research, because that's how you make progress. So the point is that, again, when the students get together in small groups, they realize, oh, most of the people are saying the same thing, that they are concerned about how they're going to do in the course, and they're actually, and that, it's a good thing. So then each group is asked to report out to the rest of the class, so one person actually says what their group was thinking, and then the students see that their group is not the only one in which most of the people were saying they were actually worried about how they were going to do. So it also kind of normalizes adversity, and it actually makes it clear to students that it's really about working hard, working smart, taking advantage of all the resources, and being deliberate in your approaches to solving physics problems that actually gets you ahead. And so you shouldn't be worried. So the idea is to reduce your anxiety, reduce your procrastination, and make it clear that students should be engaging with those problems that are not necessarily easy to solve.
Thanks.
You're welcome.
I'll come ask one too. Thank you so much for your talk, Chandra. This was amazing. And I'll say I have used that ecological belonging activity. It's fantastic. I've had plenty of students come and comment on it afterwards. But the question I had for you, we've been working on sort of how do we get some of these materials and ideas into K-12, and a lot of that based on a framework that you and others have worked on, which is great. I think one of the things that we've struggled with, and I know you thought a lot about this, and I'd love to hear your thoughts on it, is as we go into K-12 and as we try to recruit students and get them excited about this, even there, we still face the issue of students not knowing this is something they're interested in and want to engage in. Like, how do we get them to grab onto it and not sort of be scared away from it? I mean, part of the tactic we've taken is trying to get it into courses, other than physics, where people already self-select out. But I think those barriers are still there, and students thinking it's hard, right? It's set fairly early. So I'd love your thoughts on how we sort of break this barrier and get them to really see the opportunities in the array of types of things are going to be able to do in quantum in the coming years.
Right, thank you. So I think that one of the things that I would say is that even at the K through 12 level, like I definitely think that there's value in starting early to get people hooked on. The other thing is that, it's very true that people who have actually more privilege, like for example, I'm not worried about my own children, even if they didn't learn quantum in like K through 12, they are going to be fine because they have a lot of role models at home and those people can actually guide them. So we really need to center the experiences of those people who don't have the same kind of privilege. So in other words, the students who, for example, don't have parents who are scientists, who might not even be college students, those kinds of people, we need to actually think about getting excited about these areas and definitely trying to make the things relevant for them, like Tim and Kevin were talking about, is very important. Like, giving concrete examples of what quantum can accomplish, what kinds of careers are available in quantum, and the area of quantum, quantum computing, it's still a pie in the sky, but the point is all the potential of quantum computing is really good. It can solve so many important problems, like in science. I'm really, as a physicist, I'm really excited about all those things. But if you think about problems related to food security, or like drug design, or other things that are really important, climate change, even, like who knows. The point is that all of those kinds of issues can potentially, we will actually, in the future, we could have a robust quantum machine learning, quantum AI, and those things could actually do something that they might be able to discover things that we have, the kind of pattern in data that we have never been able to discover using just regular machine learning. So the point is that, giving some concrete examples of the kinds of things that quantum can do, and also having them play with some activities that kind of grab their interest. So there are lots of cool experiments that one can actually have students do. Like, for example, you can even do those things with polarizers, have students do polarizer experiments where they can actually see how putting a third polarizer in the middle actually can make the light pass through, whereas two orthogonal polarizers didn't have anything passing through. And then have them think about, hey, what if we had just a single photon going through this, not a full beam of light? How would these things change? And that could kind of make them connect, think about not like, not like classical beam of light, but making a slow transition to the quantum. The fact that even with single photon, now you're talking about probability of the photon going through or getting absorbed. But what happens, like when a large number of single photons have gone through, it's this results look very similar. But then talking about how, for example, all of the quantum communication, how that's going to actually change things, for example, quantum sensing. Quantum sensing is a thing that you can really talk about in K through 12, because their sensing applications are really already out there. Like there's so many applications in LIGO, and like just US Navy, Army, Air Force, they're all using sensing applications, and maybe many of them are from the first quantum revolution. But the point is, now we are thinking about how to actually use entanglement in ways that can actually improve the kind of sensing that we can do, and so have its applications, have sensing be more precise. The fact that all those standards of length, mass, and time now, like they are all done in quantum mechanical way, because at some point, we were using Kibble balance, we were able to measure Planck's constant to the precision that we said, okay, let's fix it now. Assume that this is so well known that there's no imprecision in this to the best of our ability, and let's define mass and everything else like this, as opposed to like having a ball sitting in France in some museum. So I feel like, giving more concrete examples and then making connection to all the application, even the quantum communication network, how, we could have a quantum network and quantum internet in the future that could really change everything. Quantum teleportation could be an interesting thing, but then again, making clear, how teleportation of information is different from teleportation of things with mass. I think that, if we think hard about how to connect it to the interest and career goals, the importance of, making it clear to students that they're very interesting and fun careers in these areas, which don't require you to be physicists per se, but something that in which you're going to actually support this quantum enterprise would be a great thing.
Thank you so much, Dr. Singh, for this wonderful talk. We really appreciated it. And I look forward to interacting with you in the future on these really exciting things you're doing. Thank you.
Well, thank you so much. I really appreciate it. Thank you so much.